Imhotep had an idea. As a chancellor, poet, physician, mathematician, astronomer, and architect to the pharaoh Dozier, ideas were nothing new to Imhotep. His writings on medicine were so well regarded that he was, 2,000 years later, deified and conflated with Asclepius, the Greek god of healing. The Roman emperors Tiberius and Claudius had inscriptions to Imhotep carved into their temples nearly 3,000 years after his death. Historical time is not the subject of this podcast, but I can't help pointing out that less time has passed between now and the reign of Claudius than had passed between Claudius and Imhotep. Suffice it to say, ideas were not new to Imhotep. Since before the time of the first dynasty of the Old Kingdom of Egypt, prominent people, including pharaohs, were buried in mastabas. A mastaba is a single-floor, multi-room mausoleum in which one room contained the sarcophagus, coffin, and the mummified pharaoh. The mastaba was a sort of mortuarial ranch house. Imhotep wanted to design something special for his pharaoh, Dozier, and the idea was to build up. Rather than a single-story tomb, Imhotep would build a multi-level affair by stacking mastabas of decreasing size to create a sort of mastaba wedding cake. 7 mastabas high, this structure, visible to this day, is known as the stepped pyramid of Dozier. About 70 years later, another pharaoh, Sneferu, had an even more audacious idea. His tomb would not be stepped, but would have smooth sides. It would be a genuine pyramid. Construction began in Meidum, a 3-hour trek south of the stepped pyramid of Dozier, and was well underway when the entire structure collapsed. The site today is a pile of debris with the remnants of the original interior at its center. Although no contemporaneous description of the collapse remains, inference may be drawn from the unusual design of a neighboring pyramid built at about the same time. The bent pyramid, as it is now known, has a comparatively steep slope that dramatically flattens partway up. Specifically, the angle of the side of the bottom half of the pyramid is 54 degrees to the horizontal, when the designers seem to suddenly have changed their minds about the angle of the walls and decreased the slope to 43 degrees, giving it the profile similar to a barn. What prompted this decision? Could it have been the experience of having built Meidum, a pyramid with a steep rake only to see it collapse? One thing is certain, no pyramid would ever be built with a slope as steep as 54 degrees. I'm Josh Young, and this is Playing Odd, a podcast about complexity and information in the natural world. Episode 7, The Riddle of the Sands. 5,000 years after the collapse of the Pyramid of Meidum, a set of researchers were also working on sand. Per Bak, Kurt Weisenfeld, and Chao Tang, then of the Brookhaven National Laboratory, were dropping individual grains of sand onto a little table. The table consisted of a metal disc standing on a metal column. Their apparatus was arranged to drop a single grain of sand onto the center of the disc, one 600 microgram grain at a time, and to repeat. As the sand pile spread to the edge of the metal disc, some grains would fall off and accumulated on a skirt that was isolated from a scale measuring the mass of the sand pile. At about 35,000 grains for a 4-centimeter disc, sand was falling off the edge at about the same rate as their apparatus was adding it, and the mass of the sand pile stabilized. This sounds like the apex of tedium and inapplicability. Has your life changed with your new knowledge that 35,000 grains of sand is the capacity of a 4-centimeter disc? But the insight of the researchers was to look at how the grains of sand fell off the edge. Early in its growth, almost all of the grains of sand in the pile stayed right where they landed. Occasionally, a grain would knock over another grain of sand and a mini avalanche would displace a few grains of the pile. As the pile grew taller and its sides grew steeper, larger avalanches would occur in which many grains of sand would fall. Once, however, the system was stabilized, with as many grains of sand falling off per unit time as the average number of grains of sand were added to the pile, a particular steepness, that is to say, a particular slope to the side, was reached. Coincidentally, this slope for their sand pile turned out to be 51 degrees, and that steeper slopes could not be achieved for any duration of time without an avalanche reducing the height and slope of the pile. The system achieved an equilibrium, but one at a state of criticality such that exceeding this threshold would cause an unpredictable but eventually certain catastrophe in the form of an avalanche. Pack, Tang, and Weisenfeld observed a number of interesting properties to what became known as the BTW, or Back-Tang-Weisenfeld model, now more commonly known as the Abelian sand pile model. The shape of this pile, dare I say rounded pyramid, was consistent when the experiment was repeated and had a characteristic slope. The system achieved criticality without any influence or design. The critical state was robust in the sense that whenever a large avalanche reduced the slope or an unusually large number of balancing grains increased the slope, the system always returned to its stable, critical state. This self-organizing criticality, as the researchers called it, seemed to arise on its own without any internal instruction set, and, more importantly for our mission, arose not as a result of any single grain of sand, but rather from the process of the interaction between the grains. In our series of podcast episodes, this is the first time that we are witnessing an example of a system that is greater than the sum of its parts. But I'm getting ahead of myself. Once criticality was achieved, avalanches would still occur, but they were of varying size. Small avalanches occurred frequently but displaced few grains of sand, while large avalanches that changed a great portion of the sand pile were less frequent. Incredibly, scientists recognized the same frequency-magnitude relationship in earthquakes, the distribution of clouds and galaxies, and vortices in turbulent fluids. This relationship is said to follow a power law and is, you guessed it, fractal. This is cool stuff, but what is its relevance to us? It is to say that the information for construction of these systems was intrinsic to the system itself. Can biological systems self-organize? Many single-celled organisms can migrate to a source of food or away from a noxious stimulus. This chemotaxis can produce quite beautiful patterns. Some of my early work dealt with diffusion limited aggregation, a fancy term for what is really a very simple process. Let's imagine a game, a rather bizarre game, that is played with a group of people who sit on a smooth floor in a circle facing each other. Each participant of the game has tennis balls with patches of Velcro stuck to their surface. One by one, the players roll a ball toward the center of the circle. By chance, a ball may come into contact with another ball and, through the magic of Velcro, stick to it. As more balls are rolled and more stick to the growing mass in the center, this mass takes on a shape. What do you think that shape will be? Will it be a disc of Velcroed balls? Will it be an irregular blob? Actually, something pretty interesting happens. The balls at the periphery of the mass act as relative barriers, and as balls stick to these barriers, they begin to form chains that branch. As the mass expands, it takes on a shape that looks vascular, or arborizing, or dendritic. We ask the same question here we did of the sand pile. Where did the instruction for this pattern come from? It is a manifestation not of any individual ball, but rather an expression that has arisen from the interaction between elements of the system. It is again a whole larger than the sum of its parts, and it required no genome to form. The pattern is genuinely self-organizing. As cells migrate toward a stimulus, they too can form patterns. The simplest and most important of these is determination of orientation. Think of a zygote, the initial bundle of cells that form after egg and sperm unite. The zygote is fairly symmetrical, and yet one end must wind up being the head and the other end the tail. How do cells of the zygote know where they are, which end they become? A theoretical framework was proposed by, of all people, Alan Turing in 1952. His idea was that a signal in the form of a chemical might be produced at one end of the developing mass of cells. Cells within that mass could then sense, by virtue of detection of the concentration of this chemical, where they were with respect to its source. Turing called these hypothetical biological signals morphogens, and it was only decades later that such morphogens were indeed discovered in that organism that is the darling of all geneticists, the fruit fly. We can think of the concentration gradient like the magnetic poles of the Earth that give the compass the direction of north or south. We actually have experience in our own lives with concentration gradients every time we smell smoke. We are in one room of the house and we smell smoke and we run around to the other rooms to see which one smells most strongly of smoke, with the intention of finding its source. What we're doing is following a concentration gradient with our nose. This rudimentary morphogen orientation signal is much more highly developed in mammalian neurogenesis. At the tip of the growing nerve cell is a growth cone that we can think of as akin to our nose sniffing out smoke. The chemicals that the growth cone detects may act over short or long distances and may be attractive or repulsive. These netrins and semiphorins establish concentration gradients and other similar signals that can be found on the surface of neighboring cells. It may not be difficult to imagine a nerve cell following the path of a concentration gradient and winding up at the correct destination. But I want to add some scale to this to show you how really incredible it is. Nerve cells may be only 60 microns wide, but they may stretch for millimeters or over 1 meter in length. If we scale this up to the size of a motor vehicle, if a neuron were as wide as a car, it would stretch for 30 kilometers. If all the nerve cell is doing in its development is following a concentration gradient, that would be akin to following the smell of smoke over tens of kilometers. This would be a bit much to ask, even of the animal with the keenest sense of smell. Indeed, the nerve has some help. Not only are attractive gradients present that direct the nerve over long distances, but repulsive ones are present as well. Also, in its propagation, the nerve does not grow directly from point A to point B, but rather passes through some intermediate waypoints in its path to its final destination. A single nerve is often not alone in its path and can also receive signals from neighboring cells. This sounds like a complicated process, but it is entirely akin to our taking a road trip. If we were traveling from Cleveland to Boston by car, we do not encounter exit signs for Boston immediately upon departing Cleveland. Rather, we see signs for closer locations that are along the way. Perhaps we see a sign for Erie, Pennsylvania, and then Buffalo, New York, and then Albany, and then finally signs for Boston. These intermediate waypoints help to guide us in our path, and there are clusters of cells past which the neuron will grow that serve the same role as the intermediate signposts for these waypoints. These shorter range directions are governed by a different set of chemicals that are short range attractants. There are also short-range repellents. Perhaps if we see a sign for a landfill or a garbage dump, we are less likely to pull off the road there. Similarly, if we start seeing signs for the city of Chernobyl or Semipalatinsk, these may act as long-range repellents as we would want to steer clear of these contaminated sites. The growth of the nerve cell is also aided by the presence of surface chemicals on neighboring cells that can also act as attractants or repellents. Imagine these to be bumper stickers on the cars passing by us on the road. We might be more inclined to follow a car with a bumper sticker that says "knowledge through science" than a car with a bumper sticker proclaiming death to intellectuals. Eventually, traffic may get so heavy along the road that we are physically constrained in our progress and follow a bundle of cars moving along our path. Neurons, in their growth, can also become parts of bundles with physical direction toward their goal. Perhaps some of the traffic will divert at Albany and go to New York City, a wise move, and we may continue on our way to Boston following the attractant of the signs indicating the direction to Boston. This is highly significant for our quest to build a complicated structure out of a minimum of instructions. In order for us to navigate from Cleveland to Boston, we did not need to first develop a roadmap. We merely had to follow signs. We will still reach our planned destination if the road veers a bit south or a bit north, as long as we follow the attractants and avoid the repellents. This is an economical use of information. And what does it sacrifice? Since the path of the neuron is not planned as one might do in a blueprint, that is to say, it is not deterministic, there will be some variability, even if the nerve starts and ends at the appropriate places. By incorporating a degree of uncertainty into the process, we can get what we need with far less information than if we were to have to encode an actual path. Here, as with our example of the hiker and gradient descent, including a stochastic element, that is to say a probabilistic one rather than a deterministic one, we are able to achieve our goal with much greater efficiency. The other distinguishing characteristic of the system is that it relies on the interactions between multiple cells, those forming waypoints and those with signals on their surfaces. We see again that our investigation reveals a process rather than an object at its center, and by incorporating concentration gradients, we are achieving some degree of self-assembly and getting some structure and achieving some degree of architecture with no instruction at all. But how far can we take this? Can we self-assemble all the way up to a functioning brain? And if we can do so, can we describe how it is done so that we can begin with our genome and end with our organ of thought? This is a heavy question, and to answer it, we will have to look at the meaning of life itself, or at least the meaning of the game of life itself, and that is what we will do in our next episode. As with our road trip from Cleveland to Boston, we have covered a great deal of ground today. We have seen that biological and even non-biological objects, when allowed to interact with each other, can produce structures of remarkable intricacy, and we call this process self-assembly. We began with systems that exhibited the seemingly contradictory properties of criticality and robustness, and were impressed that all of this happened without external intervention or any set of instructions. We saw biological systems that incorporated self-assembly through the use of concentration gradients and exchanged some degree of variability for a large degree of information efficiency. Most significantly, we were introduced to systems in which the whole is more than the sum of its parts. I want to thank you, kind listener, for taking this journey through complexity with me. A bibliography for this episode, along with links to additional material, can be found at playingodd.com. I hope this program will serve as an opening to a broader conversation. Please write to me with your questions or comments at josh@playingodd.com. Looking forward to spending time with you next week. I'm Josh Young.